Merhabalar tüm dinleyicilerimiz ve değerli konuğumuz, hoş geldiniz. itu.ai seminer serisinin 2. senesinde ve 2. konuşmasında sizlerle birlikte olmaktan çok mutluyuz. Bugün sizlerle birlikte olan çok sevgili ve değerli konuğumuz, çok pardon bana yankı yaptı arkadan, o yüzden kapattım. Değerli konuğum Profesör Asu Özdağlar. Asu Hoca'dan bahsedeceğim. Önce kısaca kendimi tanıtarak başlayayım. Ben Gözde Ünal, İTÜ Bilgisayar Bilişim Fakültesi'nde bilgisayar mühendisliğindeydim. Geçen seneden beri de yapay zeka ve veri mühendisliği bölümü kurucu profesörlerinden birisiyim. 2018-2020 arasında da itu.ai Merkezi'nin kurucu direktörlüğünü yaptım. Bugün itu.ai Merkezi seminer serimizde çok özel bir konuk hocamızla birlikteyiz. Profesör Asu Özdağlar. Kendisi MIT bölümünde 2003 senesinden beri öğretim üyesi, MathWorks Professor of Electrical Engineering and Computer Science pozisyonunda ve halen de o büyük bölümün, fakültenin bölüm başkanlığı. Bir yandan Schwarzman College of Computing'de dekan yardımcılığı görevini yürütüyor. İlgilendiği araştırma konuları bugün de bizlerle paylaşacağı optimizasyon kuramı üzerine. Özellikle non-linear programlama, convex analiz, game teori, optimizasyon, bunların haberleşme, sosyal, ekonomik ağlara uygulamaları üzerinde çalışıyor. Bu çalışmalarından birçok ödülü var. NSF Career Award, 2008 Donald Ekman Award, Class of 1943 Career Development Chair, 2014 Spira Teaching Award, bunlardan sadece bazıları. Bugün burada onunla olmak benim için ayrı bir mutluluk. Kendisiyle ortaokul ve lise yıllarından başlayarak üniversitede devam eden ODTÜ Elektrik Elektronik bölümünde uzun bir arkadaşlığımız var. Çok gurur duyduğumuz değerli sevgili meslektaşım Asu hocamız bize bugün makine öğrenmesi ve optimizasyonda Robustness ve Minmax yaklaşımları üzerine son zamanlarda yaptığı çok ilgi çekici çalışmalardan bahsedecek. Sözü kendisine devredeceğim. Bir iki hatırlatma: seminerimiz İngilizce olacak. Sorularımızı seminer sonunda soralım. Lütfen YouTube chat penceresine o hocamıza aktaracağız. Sevgili hocam, Asu hocam, we can switch to English at this point. We're looking forward to your exciting talk. The floor is yours.
Çok teşekkürler Gözde. Bir şey daha diyeyim Türkçe başlamadan önce.
Tabii ki.
Olmak korkunç güzel. Ve Gözde ile birlikte olmak da çok çok güzel. Söylediği gibi bizim arkadaşlığımız çok çok eskiye dayanıyor. Kendisini görmekten çok mutluyum. Hepinizle birlikte olmaktan çok mutluyum. So let me quickly share my screen so we can get to it. And then hopefully this will work with full screen. Excellent. So I'm happy here to talk about some of our recent work on Minmax optimization. And sort of Minmax optimization is a topic which is very dear to my heart. It's one that I worked as part of my PhD work a long time ago. But it has attracted much attention recently because of robustness issues, generative models in the context of machine learning. And I will try to basically argue today that the Minmax formulations form a canonical backbone, a systematic framework for addressing some of these issues, for designing algorithms for such systems. And I will focus on some of our recent work, some systematic insights on how we can actually design and analyze these algorithms, and some performance guarantees. And before I forget, this is, of course, joined with a number of very brilliant people, students. Ali Reza, Farzan, Sharat. Farzan is a postdoc at MIT on his way to become a professor, as well as a former postdoc of mine, Aryan Mokhtari, who is now a faculty member at UT Austin. So we all start with the huge promise of AI and machine learning. These methods hold great promise, of course, motivated by great advances in deep learning methods, immediately applied to image processing tasks, image recognition, speech processing, games, using reinforcement learning techniques, but also becoming indispensable technology in safety critical applications involving, ranging from self-driving cars, medical diagnostics, just, a few examples. The promise is great. The success stories are great. But at the same time, machine learning methods fail drastically, especially when deployed in environments that differ from those used in training. And here on this slide, so I just say it's a robustness challenge, I wanted to highlight 3 possible changes in input data to, domain shifts or task objectives. So the first one is about changes in input data, and much of the literature in this space focused on the so-called adversarial examples. And these are basically inputs generated by getting an image and adding very, very small. This is the 0.005 here, and imperceptible to human eye, but worst case perturbations, such that the perturbed image results in the model outputting an inaccurate prediction with very high accuracy. So this has attracted a lot of attention, but this is not just of academic interest. If you think about this example that I've picked here, by just subtly altering a speed limit sign, by sticking some tiny stickers on it, the Tesla's camera system reads it as 85 speed limit as opposed to 35, creating huge safety challenges. Similarly, of course, domain shift is an important aspect. You're thinking about training the vision system of a self-driving car, for instance, using standard images of traffic lights on vertical stands, and you want it also to perform well under domain shifts such as horizontal traffic lights in Texas. And similarly, this is Google's medical AI sort of not performing well when it's translated into real-world medical practices. And other sort of changes also involve, when you have different tasks that you would like to adapt to. So you have a model that sort of maybe has this, was trained on this environment for object grasping with high accuracy and success. And then you change sort of the task under which it's sort of performed slightly, and the success rate goes down. So you actually want, this is not desirable. You want your model to adapt to these changes gracefully and, do not lead to such degradation in performance. So what I'll talk about today is sort of a couple of approaches for dealing with such robustness challenges. I will start by, as I mentioned, the Minmax approach. And I will use this formulation to think about how we can both design and analyze training algorithms, Minmax optimization algorithms. And this is mostly focusing on, training performance, optimization performance. But of course, we're designing learning algorithms. We want them also to perform well on unseen environments and tasks. So we're talking about generalization properties, and I will talk about some of our recent work on thinking about how actually the choices or the design of algorithms impact the generalization properties of the resulting models. And then in the second part, I will hopefully have time to talk about how we can deal with robustness to multiple tasks or task adaptation. There's multiple approaches for thinking about task adaptation. I will focus on a model agnostic and optimization based approach or meta learning. Perfect. So let's get to it. Again, as I mentioned, I will think about as the first step robust and generative training, and take the Minmax approach as a systematic way of designing some principled learning algorithms. And if you think about, the backbone of robust algorithms is a sort of, here I'm trying to sort of abstract it away a bit, is a Minmax problem whereby we're minimizing an objective function f over x. So x is our model. And this is also parameterized by some y, and you want to do this optimization over worst possible values of y. So this is actually a very canonical formulation in optimization. It emerges in worst case design, robust optimization, duality theory. Here we're going to see, machine learning problems that can be formulated using this formulation. And what is the solution concept for such a problem? It's sort of there is no optimum here, so we're literally looking for an equilibrium or a saddle point, some x star, y star, such that x star achieves the minimum when you fix y star, and y star achieves the maximum when you fix x star. So this is sort of like a Nash equilibrium concept where you're looking at unilateral deviations on one of the decision variables. And the standard method for computing this kind of saddle point, the first thing that comes to mind, especially if you've been working with gradient descent, stochastic gradient descent, is just a slight extension of it, which is sort of this simultaneous gradient descent ascent, where, you know, in the X space, you're trying to minimize, you're taking a single gradient step. In the Y step, you're trying to maximize by taking a single gradient step, but this is simultaneous. So this looks like a very innocent looking algorithm, and you know, before I start talking about it, it's very rich in structure. It can lead to all kinds of weird behavior. It goes back actually very old. the sort of it has connections all the way to the mathematical economics literature in the seminal work of Arrow, Hurwitz, and Uzawa, who studied continuous time versions of these methods. And the convergence or stability results are mostly for strictly convex, strongly convex type of functions, which need not hold in the applications that we're considering. So that's sort of, but I mean, if you're interested in this topic, this is sort of a edited volume, which contains a lot of beautiful analysis and ideas that, one may need to look at. So let me now maybe give a few examples of where min-max problems arise in machine learning. I've already talked about adversarial examples. Here is this, everybody has their favorite example. This is one that I use. So you have the picture of a pig here. You use a state-of-the-art classifier, which correctly classifies it as pig with 91% accuracy. You add some imperceptible noise. To human eye, there's no change, but the same classifier labels it as an airliner with 99% accuracy. I'm using this example because, we sometimes say this is the example that shows machine learning makes pigs fly. So it's just a story that my son likes. And, after seeing this, he actually said, I will definitely be a machine learning person when I grow up. There are a lot of, interesting counterintuitive examples around this kind of perturbations. And to sort of think about how we can actually train our models to protect against such perturbations, let me just maybe focus on a special case, a supervised learning classification problem. Let's assume that we have this probability distribution P over the pairs, input pairs, over the pair W, where W is the input. Just think about it as this image. Theta is the corresponding label. And you're interested in choosing your model X. This is sort of, you parameterize your model by these, by this X. And you try to minimize some expected loss, where the loss represents sort of how different your model is from the input data. So this could be a quadratic loss or any other logistic loss that you can think about. So this is the standard training. We just try to find the model that minimizes this loss. When you go into robust training, what we want to do is we want to adopt a model for modifications, perturbations. And one model that sort of attracted quite a bit of attention in the literature is a paper by my colleague Alexander Maggi from 2017, whereby they represent these modifications in terms of L-infinity perturbations, Y of the data points W. Just think about these as sort of pixel-wise perturbations for the input image. Of course, I think this is an excellent question of, why do you model it this way? What is the right way of modeling uncertainty and so on? And that's an active area, of course, that which I will not talk about in this talk. But given that kind of model, the robust learning problem then amounts to, just like the standard version, choose the model to minimize now an expected loss, but this is a worst case loss, where the loss actually can take the worst possible value over the allowable perturbations in your perturbation set S. So this is sort of where min-max immediately jumps at us and requires us to develop algorithms to be able to solve this kind of problem. The second place where min-max problems arise is the generative adversarial networks, or GANs. And here the goal is to learn the input data distribution using some observed samples x1 to xn. And GAN formulation addresses this question by formulating it as a zero-sum game between two players. These players are neural networks. One of the players is a generator, which generates real-like samples from some random input, mimicking the input distribution. Whereas the discriminator here, it's another neural network, tries to distinguish the generated samples from the real samples. So it's like a game that, one is trying to generate, the other one is trying to discriminate. Everybody is trying to do their best. And this is clearly a min-max problem, right? You have two players. One is trying to minimize over G, maximize over D, some loss function. This is the original loss function used by the seminal paper by Goodfellow et al. In 2014, which looks at the classification problem which looks at this discriminator and models it as a classifier with multinomial logistic loss. It's a little bit sort of, I think, takes a leap to understand why this kind of input distribution learning problem can be formulated as a min-max problem. And there, I think I just want to highlight that one can show that this formulation actually amounts to, the generator's problem amounts to minimizing some divergence measure between the input distribution, the true input distribution, and the generator distribution. So this formulation leads to some form of divergence measure. In the context of Goodfellow, it was the Jensen-Shannon divergence. It could be other divergence measures also. So that's sort of like the natural way of thinking about this distribution learning problem. So from an optimization perspective, the issue is that this is a very hard problem. It's a non-convex, non-concave min-max problem because both the generator and discriminator are neural nets. And you see the difficulty of, training models using this approach. The first one that everyone highlights in empirical literature is that the GAN training, where the generator and discriminator are trained using these gradient steps that I talked about, suffers commonly from instability. And so this is an example where the training set is this celeb A, pictures of celebrities. And the goal is to generate celebrity-looking pictures. So think about, I guess this is how celebrities look like. So you start training this GAN model. It seems to be doing well, but all of a sudden the performance degrades significantly. So that's the instability that people seem to be highlighting. The other one that's another very interesting phenomenon. Again, I will not have time to talk about in this talk, but that's another interesting problem that emerges in these training GANs is the mode collapse. And the issue there is basically not so much instability, but rather what kind of images do you generate? So the goal, for instance, could be generating bedroom images, yet the output of the GAN training yields some this kind of behavior where it only actually keeps a few modes. So it doesn't excite all the modes that you're interested in. This is, I think, only, you can see that there are 3 kinds of images here only. So that's sort of the mode collapse behavior. Okay, so I think the point of all of these examples is just to show that we definitely need to understand this better because although these things, generate very exciting results, fundamentally, there are some issues that need to be addressed to make sure that they can perform in a robust and reliable way when they're deployed in real world. So to do that, I actually I will go back to my roots. I will just show you a very simple problem where actually these training methods could perform very poorly. And that's basically think about the simplest problem you can think about for min-max, x prime y. This is a simple bilinear problem. The solution, saddle point for this problem is 0, 0. So the goal is to use gradient descent ascent so that this actually converges to this 0, 0 point. So you don't need to do any fancy analysis here. You just write down GDA updates for this problem, which is, remember, along x, we were moving in the negative direction of the gradient with respect to x. And that's gradient with respect to x of this function is just y. And the gradient with respect to y is just x. So these are the updates. And if you add these up, square and add them up, what you get is basically, you can immediately see this x square plus y square is equal to you get an x from here and then eta square x from here. So it's 1 plus eta square x square, 1 plus eta square y square. Eta square is clearly positive. This is clearly greater than 1. So this actually diverges, not converging to 0, 0. It actually just goes to, becomes unbounded. So that's not the behavior we want. So then that sort of immediately, raises red flags. How do we then train these models? So what kind of algorithm? If the algorithm cannot perform well, even on this simple example, what do we expect it to do on these complicated problems? So a popular variant, and this is actually the reason I got interested in this area again a couple of years ago, is this sort of so-called OGDA, optimistic gradient descent ascent method, or GDA with negative momentum. I basically went to a talk given by my colleague Kostis Daskalakis, where he introduced this method and actually showed that this deals with some of the issues that I've tried to highlight with GDA. And what this method does is also very simple. So if you forget about this blue part first, just look at this black part. That's actually GDA. It's just 2 times the step size, but it's exactly doing gradient descent ascent steps. What it's doing on top of it is it also takes a gradient at the previous point, and it basically pulls you back according to the gradient in the previous point. So I tried to here give you a pictorial representation of this. So you, instead of moving in along the direction of the gradient, you also go back, and it's actually quite easy to see that if you have these limit cycles or things that are actually making you diverge, this kind of momentum, negative momentum, dampens this, right? And then the hope is that it will actually get you to X star, Y star. So when Kostis talked about this, he said, well, this was introduced in the context of, this was used in the context of online learning by Sasha Raklin and some co-authors. It turns out this is also actually a method that was introduced by Popov in 80s. And, I think right after this realization, I was very intrigued that this kind of method would work. And, one other thing Kostis said was this important that this step size should be twice the other one, which I did not understand why that would actually work. In this kind of, very strict conditions on the step size rule, we don't see it in general in analysis of these algorithms. So that motivated us as well as a number of others to sort of try to understand the convergence behavior of this method. And, there were a couple of papers looking at bilinear strongly convex concave cases. Indeed, OGDA, for the example that I just showed you, beautifully converges to 0, 0. So that just little modification fixes this problem with this algorithm. So to understand that, I will just, step back a little bit, and I will talk about this in more detail in a second, but I will just look at it using the lens of another very popular method called proximal point methods. This was introduced by Rockefeller, actually also in Martinet's work in the 80s for minimization problems, but also for Minmax. You can see it in a couple of the papers. The idea of proximal point, I will introduce it in more formally in a few minutes, but for essentially think about this as very similar to GDA, but instead of taking steps along the gradient at the current point, you actually do this look ahead. You actually look at the gradient at the next point and then move along the next point. So it's, of course, not an implementable algorithm. This is not a causal algorithm, right? You have to do some, operator inversion in general, and it's not for nonlinear functions. You don't implement it this way. But for the simple linear problem we're actually considering, you can do that. And you can see that actually this sort of look ahead immediately fixes this contraction property and makes this algorithm converge. So that's just showing that proximal point converges. And the realization we had in our work was just to say that, well, if you actually plot the trajectories of OGDA and proximal point, it looks like OGDA is following proximal point. And their convergence paths are very similar. So basically, that's what I'll try to use in the first paper that I'm going to talk about to present an analysis of this OGDA method as an approximation of the proximal point for finding saddle point. And we will show even for the convex-concave case, remember that case where things were diverging, that OGDA actually makes the iterates remain bounded and actually converge to the saddle point at a rate of 1/n. And then I will talk about another method. These are all, very disparate looking methods that people were using in practice. Extra gradient method is also a very well-known method in optimization literature. But I will show that you can also actually analyze that exactly using this viewpoint as an approximation of this conceptual algorithm, the proximal point algorithm. And then I will turn to the analysis of generalization properties of these min-max algorithms using some very nice framework, algorithmic stability, that goes back to Busquet and Elisef in the learning theory literature. So let me first start with very quickly, and I hope I'm doing okay with time. Okay, so I will just quickly give you a flavor of how to analyze these kinds of algorithms. If you're passionate, I love design and analysis of algorithms. So this is just one idea of how one can actually extract some convergence rates for these kinds of min-max algorithms. So again, this is just formalizing some of the things I already talked about. We're looking for the saddle point of this problem. We're going to focus on the convex-concave case. By that, I mean the function is convex in X for every possible value of Y, as well as it's concave in Y when you fix X. We have some smoothness assumptions. We assume that this function is continuously differentiable in X and Y. And also, we assume that the gradients are Lipschitz, and L denote their Lipschitz constant. So this is everything I said. X star, Y star is the saddle point. F star is the value at that saddle point. So let me go back to proximal point. Remember, I introduced it to you as something that looks ahead. Formal sort of description of the algorithm is as follows. You take your function, you regularize it around the current point. So this is sort of the regularized version of the original optimization problem. And you take a min-max of that regularized problem. And if you actually take the optimality conditions, if you take gradients, just think about take gradients set it equal to 0. These are unconstrained problems. Then you can show that the optimal xk plus 1 exactly satisfies what I mentioned in the previous example of, you move from xk in the direction of the gradient at the next point. And one can show that, actually, I'm not going to go into the details of this. In the literature, you can show that this kind of method has a convergence rate guarantee of 1/n, meaning both, this is sort of the so-called duality gap. Both, so x hat and y hat are the iterates you're generating. And these are ergodic iterates, actually. I don't know if I define them, but these are iterates. So think about xk, x1, x2, x3, and you're taking a time average of these iterates, and we call those the ergodic iterates, which are the x hats and y hats. And those values basically converge to f star at a rate 1/n. N is the number of iterations we have. So with n, you go to 0 at rate 1/n. And d and eta is the step size, and d here is basically just some constant that shows how far you were with to start with. X0, Y0 is your initial point. So the quick realization, I think, for us that helped us analyze OGDA was just to think about this gradient at the next point, and actually approximate it in the crudest possible approximation you can think about. So this is the gradient at the next point. Just write it as gradient at the current point, plus think about an increment that you have in your hand as the difference of the gradient at the previous point, at the current point minus the previous point. When you actually plug in this approximation of the next gradient into the proximal point update, you immediately get basically this expression, right? This is our now gradient at the next point, and it immediately gives you this minus 2 times the gradient at the current point plus the gradient at the previous point idea. So this is sort of the first thing that we were like so happy to figure out. Very simple, but what OGDA is doing is nothing but really approximating that non-causal term in the proximal point method, which causes issues with its implementation and makes it implementable. And the other thing that sort of, I think we used the viewpoint to understand is that even though you do this approximation, and it's an implementable version of the proximal point, you do not lose from the convergence rate. You actually get the same kind of, fast performance that proximal point provides you, while, even though you're doing an approximation in being able to have an implementable version of the algorithm. So just like the guarantee I talked about before, the iterates generated by OGDA satisfies this kind of guarantee that it goes to 0 at rate 1 over n. Okay, so I will maybe take a few minutes to just show you sort of how one can actually get these kind of performance guarantees for these algorithms. So this is actually very similar to how we analyze stochastic gradient descent, right? We get a gradient descent method. We view the stochastic gradient descent as a version of gradient descent with errors. So I will basically do the same thing here. I will say I'm going to analyze a proximal point method with error. The error will be with respect to how OGDA approximate proximal points. I am now, just cleaning up some of my notation. I just call X and Y as Z. So this is now a vector that sort of includes both of my decision variables. And then, I also write down as this operator F as the gradient with respect to X and Y. And for OGDA, then I'm not going to go over the details of this. I just want to give you a flavor of the analysis. If you just write down, proximal point minus OGDA iterates, the error you incur takes the form of this. So it involves the gradients at the k plus 1, k, and k minus 1 points. And the key sort of idea for analyzing proximal point is a little different from gradient descent, because in gradient descent you use a Lyapunov function, which is either the function difference or how far you are from the optimal point. Here there is this three-term equality, which is in Bertsekas's optimization algorithms book. This is sort of the key idea or relation that you write to analyze this algorithm. And that sort of relates somehow this inner product of the gradients and the zk plus 1 minus d, and all these, difference of the current point from some z, k plus 1 from z, difference between k plus 1 and k. And when you have, this is sort of the first three term is exactly the three-term equality for proximal point. If you have errors, you basically have this error term, which is represents the error for any error, but we're going to just, plug in the corresponding OGDA here to be able to get our rate result. Okay, so once you have this relation, this is just a couple of lines to actually to prove. So please take it for granted. But then you can start massaging this relation. Suppose now we're going to add this from 0 to n, right? The beautiful thing here is when you add both sides, you get a lot of telescoping here. K's and k plus 1s cancel out and leave you with z0 minus v minus vn minus v. So many of the inner terms just cancel out. And then you have this n minus 1 and this other term. So using the Lipschitz continuity operator of this operator f, you can relate this fzn minus sdn minus 1 to the values of the difference between zn and zn minus 1. And then if you clean it up, basically, you end up with, being able to bound the term on the left-hand side with the z0 minus d square minus some positive term. So that immediately so one other thing to notice, of course, is that because we're looking at the convex concave case, the gradients satisfy monotonicity properties. Therefore, this left-hand side is always non-negative. So if you actually, this is greater than or equal to 0. So if you just pass this Zn to the left-hand side, you immediately, can see that the iterates of this algorithm is bounded. So I'm probably going into too many technical details. I just want to give you a flavor of how you actually analyze these kinds of algorithms to show boundedness properties and how you extract a rate from there. So boundedness is, I think, on this slide. Then the next thing to show is how can I get a rate result? So again, here we use the convexity concavity as well as this averaging, trick that is heavily used lately in the analysis of these optimization algorithms. And that is basically just to realize that for convexity concavity gives us that this inner product relates to the function values this way. And moreover, the sums, because of, again, convexity, actually can be bounded from below by function values at the average of the iterates. So average of the function values is greater than or equal to function values of the average iterates. So this is just being able to write, how the average iterate's function value behaves, using this kind of analysis. So when you put now, remember, we were actually summing this up from 1 to n, which is summing this part up from 1 to n, which now, because of this averaging trick, can be reduced to, a guarantee on the function value at the average iterate. So that immediately gives us this sort of bound on this duality gap as a function of this sum over this inner product. And if you go back, this is just now if you're summing and dividing by 1 over n, so that you immediately divide this by n, and then you remember this radius of how far z0 was from z star, and that immediately gives you d over n type of result on the right hand side. So this basically gives us sort of a very simple rate analysis for these kinds of algorithms. And let me also quickly mention extra gradient method, because this is also used in practice quite a bit. This is, as I mentioned, I think is showing up in the recent literature more and more, but it actually goes back to another very prominent paper in optimization, which is by Korpelevich from 1977. It's another very weird looking algorithm. I can never remember how to write this down. Let me just start by saying that. So that's why I made a picture for you, so that hopefully this will stick in your head. So the idea here is a little weird. So you start from some xk, you take a gradient step, just like gradient descent, along gradient of f of xk. That's your middle iterate. So it creates this middle iterate, and then it computes a gradient at that middle iterate, goes back to the original point and moves along this middle iterate gradient. So, very interesting. Why it works is, again, I think you're doing some look ahead, right? Sort of we're going into the same idea. But I think the exciting realization, at least for us, was to show that if you try to write down this middle iterate gradients and how the algorithm evolves, actually it takes this form, just a couple lines to show that. You can write it as going from the previous middle iterate to the next middle iterate, and using, you have this kind of term here. But then this kind of term, you can again think about a way of, again, approximating gradient at the next iterate, right? This is the previous iterate plus some increment that you learn from your current and previous point. So basically, EG is again nothing but a proximal point method, but on the evolution of the middle iterate. So once you have this understanding, basically, again, you do the same kind of analysis. You can show that it again has this 1 over n convergence. This actually rate was shown in a very seminal paper by Nemirovsky in 2004 under some conditions and using a completely different approach, some variation inequality approach. This, I think, just allows us to get this kind of result in a very general setting and using very simple analysis. And I hope I was able to convince you that sort of once you have this, interpretation of all these algorithms coming from some, conceptual algorithm, then you can actually get a lot of leverage in terms of analysis and getting results, performance guarantees for these kinds of algorithms. So that's sort of what I wanted to say on the optimization side. Let me quickly say a little bit more, because much of the literature, if you look at, Minmax, there are a number of recent Minmax papers, some from Berkeley, Jordan's group. There's some that are looking at local stability type analysis. They're all about whether or not this algorithm converges. And that's what I talked about as well. You have a well-defined algorithm. Do I converge to the optimal point? But of course, we want to understand more than that, because our goal is to design learning algorithms that can generalize from empirical samples to unseen test samples. So to do that, I will very quickly, because I'm running out of time, I also want to talk a little bit about meta learning. And this is something I recently learned about, and we're used. I really think it's a very powerful approach. So the idea is, our goal is to write down generalization bounds, error bounds for these learning algorithms, and for the algorithms. But first, how do we define this generalization bound? Basically, it's the expected difference that your model between the error that the model incurs on training samples minus the error that the model incurs on a new unseen example Z, which is drawn from the distribution that generates your training set. Okay, so that's sort of the usual generalization bound that we are trying to sort of bound. And for an algorithm, you can define the same bound as it's the bound corresponding to the model that is learned or outputted by this algorithm. So the idea is to use basically this algorithmic stability framework, which was defined by Busquet and Elisev, but also refined in a very nice paper by Hart, Recht, and Stinger to study generalization error of iterative algorithms. And the idea is the following. If you can show that a min-max optimization algorithm is epsilon uniformly stable, and I will define that in a second, then that guarantee, epsilon uniform stability, immediately gives you an expected generalization risk. And what epsilon uniform stability is for an algorithm, you basically get any two data sets, S and S prime, they differ in only one sample. Then you basically use your algorithm on these two data sets. You look at the learned models, and the algorithm is called epsilon uniformly stable if the learned models produce approximately the same prediction. Okay, so a change in one data point doesn't, completely get your approximation, your prediction to a different point. So. Again, as I mentioned, this was done in Hart, Recht, and Stinger for minimization problems. We sort of considered this kind of approach for min-max problems. And I just want to point out why I like this approach very much, because these generalization guarantees generally, or rely on learning theory-based approaches. And generally we try to come up with some, uniform convergence of empirical quantities to their means. This is a little different approach. Basically, I view it as a much more sensitivity-based approach, whereby you vary the input and you try to understand how it influences the output of a learning system. So, and that's what we need, right? Sort of to be able to understand, this is exactly the generalization guarantee that we are after. So, and the nice thing is you can actually get this generalization guarantee by just focusing on this epsilon uniform stability properties of the algorithms underlying these learning models. And there's a very nice also connection to stochastic optimization here, but I will skip that in the interest of time. Just quickly, stochastic gradient descent or stochastic approximation theory very much aims at getting some, when you say convergence estimates there, it's very much about this sort of difference from an optimal population risk. But, the issue here is these kinds of methods generally look for fresh samples. When we apply our algorithms, we generally run it over, multiple epochs of the training set. So we don't use fresh samples at each point. So algorithmic stability actually allows us to get something more general than what was considered in this literature by, combining both stability as well as optimization errors. Okay, so I will very quickly, sort of how do we analyze stability properties of gradient-based algorithms? It goes through two. Remember what we were trying to do, right? We have two data sets, and they differ only at one point. So the goal is to understand. I apply my algorithm to the first data set and the second data set, and it generates some iterates, right? The limit point of those iterates is my model, the learned model. So what I would like to understand is how these two algorithms diverge from each other because of this single data point that differs in my data sets. So in order to understand that, there are two steps. The first one is to understand how a gradient-based update rule expands your iterates. So you start from some xy. You apply a gradient step g of xy. If you start from x prime, y prime, and apply the same update, how much do they differ from each other? So that's sort of the expansivity of an update rule that one needs to, figure out. And you can show that under the properties of your objective function, smoothness, concavity, and so on. The gradient updates actually cannot be overly expansive. Actually, for strongly convex concave functions, they're contractive. And you can also write similar things for the proximal point method. The other thing is just another lemma which says, the previous one was just, using the same update rule, same gradient rule. If you actually pick that data point which is different in the two data sets, you will actually apply two different rules because that will mean two different gradients applied to the points that you're generating on the two sides. So one needs to also understand if you are applying two different updates, how your iterates diverge from each other. And that's this growth lemma. And then, once you have these two, you can show the stability of any algorithm. So you're trying to look at its output on two data sets that differ only in one sample. Let's maybe to understand the idea, consider the stochastic case. So you select an example which is identical in these two data sets, then iterates just diverge with the expansivity of the same update. And if you select a non-identical example, you just use the growth lemma to see how much they can diverge from each other. So that was the sort of technical background on how you analyze, stability and how you actually find this epsilon uniformly stable property of the algorithms. So what we did is we basically used this kind of approach to understand GDA versus GDmax. And these are, algorithms that are used frequently for training GANs or adversarial training. In particular, GDA-type methods are used heavily on training GANs. GDmax is the standard optimization method for adversarial training. And we wanted to understand, different literatures for different papers use different algorithms. So how can we actually compare the generalization properties of GDA versus GDmax? And I did not, define GDmax. Was GDA, remember, was just these simultaneous gradient updates. GDmax basically just assumes that the max is available for any x. Okay, so it's actually, of course, you can't implement this in practice. What people do is, instead of this max, think about having maybe 100 or 1,000 gradient steps instead of one step each. So the inner loop contains 100 or 1,000 steps. So I will quickly tell you about our results. So for strongly convex, strongly concave case, the two actually behave very similarly, GDA and GDmax. So I will not spend much time on that. But for non-convex problems, something interesting happens, and it turns out, depending on how you choose the parameters of your algorithms, the generalization bound for GDA actually outperforms the generalization bound of GDmax, implying that if you actually simultaneously train these models using single update in X and single update in Y, as opposed to doing 100 or 1,000 updates on the Y space, you actually leads to better generalization. And this is sort of some theoretical support for some of the findings in recent papers that says GDA seems to be actually generalizing better compared to this GDmax. And we did some numerical analysis. This is a strongly convex concave case. The performance is not too different, but this is super interesting. And I really think this is sort of we're just scratching the, surface here, because this is really, beyond the theoretical analysis and some empirical studies, I feel like there's much to understand here. For the non-convex, non-concave GAN problems, we basically simulated two algorithms. On the left is GDA, and on the right is GDmax. And to implement GDmax, as I mentioned, we did 1/100 atom here, and this is 1 atom on the left-hand side. And you can see that red is here the training error, blue is the test error. The GDA beautifully, training and test, follows each other, converges to 0. Whereas with GDmax, the test performance completely, does not follow the training performance. So you see a big gap, and essentially showing that you don't get good generalization performance by using this kind of algorithm. So, this is just, I think I wanted to share with you. This is very hot off the press result for us. I think there's much to do here. If there's interest, I'm happy to talk to students interested in this, because I think there's much more to understand, especially in the non-convex, non-concave setting for these kinds of problems. Okay, so in the remaining few minutes, I will just want to move to another robustness notion that we would like to have in our sort of trained models, and that's sort of when you have multiple tasks, and you have new tasks which may actually come with limited labeled data. How do you actually learn these new tasks? So the issue is, when you have limited labeled data, we can't use the traditional methods that I've been talking about, because these require massive amount of labeled data to be able to train rich models. So the question is, can we use prior experience to be able to adapt to new tasks efficiently? And humans are great at this, right? So if you know how to ride a bike, you quickly learn to ride a motorcycle with just a few trials or less trials compared to just learning to ride it. So the question is, how can we actually embed this kind of capability or into the methodology? And a very prominent approach for task adaptation is meta-learning, or learning to learn. So can we use data from previous tasks to learn, update rules or model parameters, but then we think about adapting them or fine-tuning them to perform well on new tasks with a small amount of data. So you can think about it as a meta-learning model at the training time is actually trained over multiple tasks, multiple classification tasks. And then at test time, it's later adapted to a new task with very few data points. And so this also sort of, I think, very much captures how humans, rapidly learn and generalize from a few examples of the same concept. And a simple approach or an effective approach here is the MAML, Model Agnostic Meta-Learning Framework, introduced by Chelsea Finn and co-authors. And we like this because this is very optimization-based, again. It's basically, it's a gradient-based method in which we train the parameters of the model in a way that later at test time, we will have a small amount of computation, optimization allowed for us, small number of gradient steps that we can implement using a few data points from the new task, and that leads to good generalization of the new task. So the idea is in the training, the meta-initialization, and then you will update it on your new unseen task to be able to perform well on this new unseen task. So this is just some schematic I put together to explain, how meta-learning sort of formulation differs from the usual, sort of empirical risk minimization type of framework that we have. So to just explain it, let me quickly, explain the notation. We have a set of tasks, Ti, coming from some distribution P. Fi here is the loss function corresponding to each of these tasks. And the assumption for meta-learning is we will have budget to slightly update our model at test time. So here, in one approach, we can just think about finding a model that does well in expectation over all tasks. Okay. And in the meta-learning, you basically assume that, again, you want to find a model that does well over in expectation, but assuming that model W that you find will be updated with some, this is just, I just used it for, illustration purposes, one gradient step. You can assume 2-3 gradient steps also, but this is sort of the difference from the original formulation. You find a model which performs well when updated on the new task. Okay, so that's sort of the meta learning formulation. And then you can go into, designing the algorithm for once you have this, explicit formulation. MAML actually runs a gradient step, very simple gradient algorithm on this newly defined cost function F, capital F now. So think about WK plus 1 is WK minus gradient along, minus a step along the gradient of F. And the interesting thing to notice here is because F is now some weird composition of these functions, right? Gradient and F. When you take the gradient of this function here, you use chain rule, and then it gives you some expression of this sort, which involves this red part, which is the Hessian. So although it's a first order method, the Hessian information comes into play if you want to apply a gradient method on this formulation. And of course, to implement it, we use basically just like the stochastic gradient descent, we approximate gradients and Hessians using batches of both tasks and data. So I need to approximate the Hessian. I need to approximate these gradients using batches of data, but I also need to approximate this expectation using batches of tasks. Okay. And once you do that, this is sort of how the algorithm looks like. This is approximating the batches of tasks. And then, these tildes are the, approximate empirical gradients and Hessians. So as I mentioned, I keep putting this part in red. It needs second order information. What Chelsea-Pin did in the paper is actually consider a first order MAML. Just ignore the red term. Okay. Once you ignore the red term, your algorithm becomes, this is MAML algorithm, this one. Okay. Just ignore this. This is exactly the gradient of Fi. The problem with that is basically, actually you can show through examples that if you ignore that second order term, your error actually does not go to 0. You can show that there's a lower bound on the error. So it leads to non-vanishing error. So what we did in this case was, okay, there's the Hessian here, that the second order information that's needed, but it's not too difficult to approximate it. I keep talking about approximations in this talk. We approximate everything and try to get good performance out of it, I guess. But I mean, the point is you can approximate the second order information using first order information. So, and that leads to our proposed method, which is Hessian-free MAML. And there are some challenges in analyzing this because it's a little different than usual gradient descent. I was talking about this Lipschitz constants, right? That Lipschitz constant plays an important role in analysis because of this again this composite function f. The Lipschitz constants here are actually point dependent. They're not constants, so they can be unbounded. So for that reason, one needs to be a little bit careful. So the Lipschitz constant that this cost function has depends on W, but also involves this expectation. So you need to design the algorithm using not a constant learning rate, but a stochastic one and an adaptive one. It should adapt to where your point is, but also it should approximate this expectation by taking batches. But then once you do that, that's the stochastic learning rate part. The other issue that emerges here is, unlike stochastic gradient descent, these lead to biased estimators. Remember, I was approximating gradients and Hessians using batches of data. Because these now go through nonlinear functions, these batches do not lead to unbiased estimates of the original gradient and Hessian. So everything is biased. So you need to analyze this algorithm with biased gradients. Luckily, we can do that. And basically, I just want you to look at this column here for iteration complexity. If you have gradient information, which has a higher runtime per iteration, you get a 1 over epsilon squared type of complexity. Hessian-free MAML still allows you to get the same kind of iteration complexity without, introducing this additional computational requirement of computing these Hessians. So maybe I'll just stop there. Oh, I this one more thing, and then I'm done. So the other thing that we're excited these days is to actually use this framework in the context of the so-called federated learning. And in federated learning, we have these edge devices, right? Many cell phones that have small amount of data. So it's not enough amount of data to learn a model on their own. But the idea is, can we actually pull this data at a central location to learn maybe jointly? But then we want to personalize this. So because if you just learn jointly, it produces a common model. So the idea is, can we aggregate this whole data to be able to learn a joint model and then adapt to each user? That's the personalized federated learning. And I just want to point out that this is just very natural place where we can use this mammal type formulation. So classic federated learning is minimizing the average of the cost function of all these devices. Personalized federated learning, you can just think about saying, okay, I will use this common model, but I will actually allow personalization at the edge node later. And this additional personalization or adaptation can be viewed as this additional computation that mammal allows in, updating the model used in these devices. So this also is another sort of, now this has to be all done in a distributed way, right? Because we don't have, in mammal, we have just single problem, single model, single algorithm. We're trying to implement the algorithm in a central processor. Here, this involves communication between these edge devices and this central location. So basically, you do everything in a distributed way, but you can both do the optimization analysis and the generalization analysis for such settings. So with that, let me maybe conclude. I find this area super interesting because I think the ideas are, I hope I was able to convince you that several of the fundamental ideas coming from optimization keep appearing in these different settings, ranging from adversarial training to GAN training to meta, multitask, few-shot, federated learning. And I wanted to give you a flavor of, how do you design these algorithms, how do you analyze these algorithms, but also I think it's very important for us as a community to think about not just optimization, but also these generalization guarantees so that we can actually, make sure that these learning algorithms perform well on seen data. I told you about mostly analysis in the convex setting. There's a lot of open questions for non-convex problems. Non-convex problems are super hard. I don't know if you'll be able to make progress on the most general non-convex, non-concave, but I have great hopes that for problems with structure, especially, for specific problems, this is the GAN problem. Are you doing federated learning in a robotics application where, your shifts in these distributions have some structure? Those kinds of problems, hopefully, we'll be able to use these ideas and still be able to get performance guarantees for the non-convex, non-concave settings. So with that, maybe let me conclude. And I haven't seen any questions, Gözde. I just thought.
The questions are in YouTube chat. There are many questions. So actually, this was a fantastic talk also, and amazing convergence and stability analysis. And really, we can all see your passion for this analysis. You were able to really pass that energy to us. The questions are in English, so it's great. I think probably it's better.
Okay. So should I look at somewhere or should I stop sharing?
Actually, maybe if you are going to show up some things, you can keep the slides on. Or if you want to also read the questions, I will be reading them to you, but let me just...
How do I read them? I don't see them now. Okay.
It's in the YouTube chat channel. I will be reading them. I'll start maybe with one or two questions. Kemal actually also asked a similar one. Because now there is this strong assumption of convex concave objective, and we work with GANs, for instance, myself, and we see all those problems you mentioned, the instability, the mode collapse, because these are non-convex, non-concave problems, and because due to these local saddle points, right? You are the expert.
Yes.
That's the problem. Like, for instance, when one of the, let's say, the generator is converging towards a local minima, the discriminator may be converging towards a global maxima, and all these things can mix and match. So your analysis, this amazing analysis, how can it maybe shed light or help with actually towards those non-convex or relaxing assumptions of the convexity in this case is our first question.
Perfect. So I did not talk about it, but I think there's some very nice papers. And actually our generalization analysis relies on that case also, because there we were looking at non-convex strongly concave. So in the GANs, the nice thing is for some GANs, we can have the non-convex strongly concave structure, right? For non-convex, non-concave, it's very difficult. But non-convex strongly concave, at least if you have some, some nice properties of the inner maximization which GAN satisfy, then you can actually, Jordan, the paper that I cited, Jordan, and the third person that I always forget, has this very nice, even great guarantees to a local Minmax point. And it's a local guarantee, but still at least it's a convergent stability guarantee, right? So it doesn't like or oscillate or things like that. So much of what I talked about can actually be generalized. Careful with this generalization part was already that. Much of the meta learning can be generalized to non-convex, strongly concave settings with local stability guarantees.
Okay.
Going to global, one needs to take a leap of faith and, see much more. I mean, why we are getting this global optimality result, even in stochastic, even in the minimization case without max, it's not.
There's an open question. Yeah. Okay.
There's the stochasticity of the algorithms, the noise introduced to the algorithms that makes them look not just like a gradient descent, but maybe more Langevin type dynamics that people have been looking at, so those sort of simulated annealing type algorithms, right? So that actually make you jump over local bumps and get global type of convergence guarantees. It's open. I don't know.
Yes,
so
yes.
Strongly concave, I have hopes that we can actually I would strongly recommend the Jordan paper, which is a very nice paper.
Okay. Great insights also. Yeah, excellent. I wonder one more thing, then I'll jump to the questions from the YouTube chat. For our problems, like in this generative learning, unsupervised learning, we typically devise dedicated auxiliary loss terms. Maybe this is a very naive question, and because now I found the expert like you, I'm asking, what about those, like when we, depending on the objective function, the trajectories, right, change. Of course, you already mentioned Lipschitz continuity, right, smoothness, but don't they also affect like the type of these dedicated losses affect the convergence?
The loss function.
Yeah, the loss maybe, like putting in terms and taking them out.
Yeah, so that impact, I was summarizing it in terms of the Lipschitz constant, condition numbers and things like that. And because it's the convex concave case that I was talking about, it's natural that those parameters emerge. But of course, in the non-convex case, those do have an impact, like the properties of the loss function very much impact the trajectory of the algorithm. And again, we need to find the, exactly the smoothness parameters, strong convexity parameters. Those are the things that affect these kinds of algorithms' behavior. So that's what we see in the performance. That's why I think also this regularized algorithms, right? Proximal point where you add this regularization, which essentially turns the problem into something with nicer structure in terms of strong convexity. That makes the algorithm perform better. So loss functions, I think the quick answer to your question is loss functions definitely impact. And that's why we sometimes try to regularize so that actually we get better performance in terms of the algorithm.
I see. So, great. So another question from Kemal, our colleague. Is it possible to extend methods like OGDA to second order optimization? Do you see any value in this in terms of computational cost versus convergence rate?
I have got that question. It's a very good question. The answer is definitely one needs to think about it. I have not seen second order versions most of the time, because these are applied in the context of deep learning. We would like to do first order, and we would like to approach. That's what I was doing even in the meta learning case. Overall,
because it's difficult to calculate Hessians, right? With these millions of parameters. Yeah.
But in terms of, if you're thinking of it as an optimization guarantee, can I get better guarantees if I actually introduce second order information to OGDA? Yes, my answer would be, but I have not seen or done how to do that in the context of OGDA.
Okay, great answer.
Another acceleration, by the way, other acceleration techniques are sort of out there. We have had some work on thinking about how we can accelerate these methods. You don't need to go to second order immediately, right? So you can also think about is there a way to accelerate? And that's another interesting question for these kinds of algorithms.
Higher order momentums, right? Also going back further, plus the acceleration terms. Yes. That's another interesting direction. Definitely.
And I'm happy to send the paper to whoever, if they can email me. We have some work in that.
That would be excellent. We will email you. And maybe continuing with Kemal's question, for generalization, what about the case where the distribution of training and test samples are different? Then would it be possible to prove stability when the KL divergence between them is bounded?
Yes, that's another excellent question. We like here, here's that paper. In this paper, which is generalization analysis for meta learning, I mean, the same ideas work out, I think, is the assumption on the algorithmic stability is the test and training distributions are the same. You can also think about in the context of meta learning, this is very natural, right? You can think about an unseen task. I mean, before you can think about, a task that you used in training time versus an unseen task. And when you have an unseen task, that's a completely different distribution. So in that case, the guarantees take the form of, think about it as what you get from this algorithmic stability bounds, plus some difference between these distributions, some divergence measure, some KL or different kinds of distribution differences, divergences. So we have something like that in this paper. Again, I'm happy to share with Kemal. I don't know. I just don't know.
Yeah. And another question is, do you see any potential applications of subgradients in this area? And actually a follow-up, what is the effect of gradient step in subgradient methods?
So that's another very good question, because from the beginning, I assume everything is smooth, right? And if you're thinking about, sparse, regularized loss functions, we don't have that. So one needs to also think about, like the problem with subgradient methods is you suffer from loss in convergence rate. You go from 1/n to 1/square root n. So what people do when you actually have that composite functions with a non-smooth objective function is this prox gradient methods. You do a gradient with respect to the smooth one, and you do some proximal with respect to the non-smooth version, which may actually have some explicit form, so you can implement the algorithm. So that there you don't, this prox gradient then doesn't lose the rate. Saying that, but I think in terms of the current OGDA algorithms that I talked about, whether it can actually, you can also do the analysis for the non-smooth case using subgradients in terms of gradients. I think the answer should be yes. I haven't done that. I don't know if it's done in the literature.
Okay, great. Another, you see, we have many questions also, but we have now a few more left. I wonder if it is possible to iteratively use interior point methods to solve the non-convex, non-concave optimization problem by approximating convex, concave functions locally to the problem. Using interior point methods.
That would be, yes, but then I think the reason we're sticking with gradient methods here is because it's, we don't want second order information. We want something simple. We want the iteration, each of the iterations to involve simple computations. If you go to interior point methods, then, of course, there's a very large literature on that. But that's not the type of methods used for these kinds of applications.
I think the reason this was asked was since those methods guarantee solving convex-concave problems, the question asks at a certain number of iterations for given optimality tolerance, it may be possible to put limits on convergence rate for some of these problems. That's a question mark.
It's a good question. I have not looked at interior point method setting. I mean, it is possible, of course, to get rate guarantees for convex-concave problems. For non-convex, non-concave, again, you go into local guarantees and things like that. But just as a conceptually, it's not the type of algorithms we use here.
Yeah. Maybe a last question by Elgiz. Is there a relation between robustness capability versus generalization capability? Would we expect if a model generalizes better, it is more likely that it will also be more robust? Robustness versus generalization.
Yes, that's another very good question. What do we mean by generalization, right? So I think there is some trade-offs that people have looked at in terms of when you're trying to get a robust model, then you lose from accuracy, right? That's one trade-off between thinking about robust models versus accuracy. But if you're thinking about for instance, you want to be generalized better with respect to domain shifts, right? I think it depends on how we define the robustness and how we define generalization. What kind of accuracy we're talking about?
With respect to task or with respect to the unseen samples?
Exactly. There are some trade-offs that have been shown with respect to robustness versus accuracy. But at the same time, if you're thinking about, particular form of like a min-max formulation that can capture these domain shifts, and then you're thinking about whether it does well with respect to these domain shifts. If that's the guarantee you're looking for, yes, robustness helps. But one needs to be careful, I think, in terms of how you define the performance accuracy you're talking about.
Great. I think that should be it. Also, thank you so much. Maybe we can switch back to Turkish at this point. Asu hocam çok teşekkürler. Sevgili dostum, meslektaşım. Gerçekten çok keyif aldık. Çok samimi bir konuşma oldu. Canlı yayındayız ama gerçekten yani o tutkunu hissettik. Çok güzel şeyler yapıyorsunuz. Bu harika konuşma için çok teşekkür ediyoruz.
Çok teşekkürler.
Senin son sözlerini alabiliriz. Neler demek istiyorsun ayrılmadan önce?
Çok sevindim. Hem seni gördüğüme Gözdeciğim hem de göremiyorum başka kimseyi, ne yazık ki. Görebilsem Kemal'le tanıştığıma çok memnun oldum. İnşallah eğer ilgisini çekerse bu konular
Kemal tanıyorsun, bizim Kemal Üre, o da şeyden hemen tabii. Hayır, ben Kemal, tamam. Tabii bizden.
Evet.
Aynen. Konuşuruz offline'da da, çok iyi olur. Çok memnun oluruz.
Görüşmeyi çok isterim.
Tabii.
Çekiyorsa eğer öğrencilerin ya da herhangi kolektif konular konuşmayı çok isterim. Çok teşekkür
Çok seviniriz ve yüz yüze de bekliyoruz inşallah. Fiziksel olarak da ağırlamak isteriz. Gerçekten harika bir seminer oldu, söyleşi oldu. Çok sağ ol. Hoşça kal. Herkese selamlar. Güle güle.